Live now. Okay, so hi everybody, and welcome to this new seminar. It will be the only one for the week because we have, as you already know, on Thursday, the research division department meeting. But today we have Bianca Neuretes. I cannot pronounce it quite right. She's coming from the Mass Bank Institute. She defended her thesis in 2023. And her main line of research is on the early type galaxies, massive early type galaxies with supermassive black holes. And in particular, she has been working with numerical simulations of M-body mergers with a realistic code named SMARTS. And today she will be talking about precisely that. So whenever you're ready, without further ado, the floor is yours.
Thank you, Daniel, for introducing me. And thank you for having me especially. I'm happy to have the opportunity to hold the seminar at the IAC today. It's my first time here and my first time in Tenerife in general. And what can I say? I'm already amazed by the beauty of your island and the friendliness of the people I meet here. My Spanish is everything else than advanced, and I only started with Duolingo a couple of days ago. But if I may, I would like to try to say something. So, buenos días a todos. Soy Bianca Neureiter y estoy encantada de estar aquí. Okay, so as Daniel already introduced, I'm currently working as a postdoc researcher at the Max Planck Institute for Extraterrestrial Physics, which is located in Munich in the south of Germany. And I here mainly work together with people like Jens Thomas, Professor Ralf Bender, Roberto Salia, Thorsten Naab, etc. And in this group, I last year finished my PhD, where I focused on the establishment of a novel triaxial dynamical modeling machinery and its application to observational data of massive elliptical galaxies. This was the reason why I called the title for this talk today, Weighing the Giants, because my main research area has so far focused on studying the most massive quad early type galaxies and their central supermassive, or other people would also call them ultramassive black holes. I would like to start with bringing you some greetings from Munich, which is not only known for its Oktoberfest or its beautiful lake and mountain sceneries, but there's actually also a lot of astrophysics going on here. So we have two Max Planck Institutes for astrophysics, the Max Planck Institute for Extraterrestrial Physics, the MPE, where I'm currently working in. We have the Max Planck Institute for Astrophysics in the neighbor building, as well as the headquarters of ESO just around the corner. We also have a Wendelstein Observatory in the Bavarian Alps, around 2 hours south of Munich, where we operate a 40 centimeter and a 2-meter Fraunhofer telescope, which is used for students' projects, but we also cover a wide range of astrophysics fields. Like, for example, we do exosolar planets physics, we do brightest cluster galaxies analysis, deep photometry, intercluster light, etc. And the data then gets always analyzed in the USM, the University Observatory, which is located in the heart of Munich. Okay, then let's dive into the science for today. I would like to start with describing what the most massive quad elliptical galaxies are. In general, if you have any questions, please feel free to ask during the talk or also later, of course, as you prefer. So in this image, we can see two different kinds of elliptical galaxies that are also called early type galaxies, ETGs. And we see that there are some smaller ellipticals marked with the blue circles, and then we have larger counterparts marked with the red circles. And when we look at their surface brightness profiles, we see that those objects clearly distinguish. So we see in red the surface brightness profiles of the most massive elliptical galaxies. And we see that their central surface brightness profiles show a shallower central slope as an extrapolation of the outskirts would suggest. And this is in contrast to the blue surface brightness profiles of the smaller ellipticals, which also show a steep profile in the central parts. And the reason for this is that the small or intermediate mass early type galaxies have some bright cusps in their center, whereas the most massive early type galaxies show a depleted, a diffuse so-called core in their center. And the radius at which the surface brightness profiles of these most massive ETGs then breaks is the so-called core radius or break radius with which the radial values are here normalized. And the origin or the fact that there is such a central missing light inside those quad early type galaxies already suggests that these objects have a different formation mechanism. The so far accepted concept is that these objects are the remnants of dry merging processes between progenitor galaxies with hold or have individual black holes at the beginning in their center. So when looking at these snapshots of such an embodied merger simulation, we see that in the beginning, we see that there is still a bright collection of stars centered around the black holes. And these cusps then get depleted with time. So at the end, last snapshot, we only see a diffuse core. What we also see is that with time, the two black holes of the progenitor galaxies approach each other more and more. And hand in hand with this goes something that is called the black hole core scouring process. And in this process, stars that get close enough to the vicinity of the black hole binary experience a three-body gravitational slingshot interaction, and by this get kicked out from the center. This then results in two things. First of all, by this, the two black holes merge, and it also contributes to the formation of the depleted core because the stars in the center get kicked out. This black hole core scouring process will also, yes, please. Yes, true. So, I mean, at some point, the black holes will completely merge, not only because at some point. Sorry, the question? The original cusp will be completely destroyed. So this is what we see in the surface brightness profile. So at the beginning, or in smaller counterparts of ellipticals, we have these cusps. Yes.
You don't recover the original cusp, so you don't tend to accumulate more and more stars.
No, the core will stay as the core is.
Okay.
Mm-hmm. Yeah. Thank you for the question. Okay. So the described black hole core scouring process will also leave a characteristic imprint on the stellar dynamics. And when we think about the concept, we can already guess which imprint we can expect, because I said that it requires orbits that get close enough to the black hole binary vicinity in order to experience such a kick out. And this will be orbits that show a large radial variation over time, like this red orbit here, which at some point in its lifetime will approach the center and will then get kicked out. By this, the two black holes again will approach each other more and more. And the second thing that's going to happen is that the center will then be depleted of these radial orbits because they got kicked out. And this leaves behind an excess of these circular-like, called tangentially-like orbits, like this blue orbit here, because they at no point in their lifetime get close enough to the vicinity of the black hole binary to experience such a kick out. In general, when we want to describe the orbital distribution inside a galaxy, we can describe it with the so-called anisotropy parameter beta that can be computed by the velocity dispersions along the tangential and radial directions. But just in simple terms, what does it mean? When we have a beta value that is positive observed in a galaxy, this will point to a radially biased central orbit distribution. So we will have an axis of radially like orbits. And then if beta is negative, this means that we have a tangentially biased orbit distribution. And in this sample here that I show you, this is a sample of cohort early type galaxies that have been observed with Symphony at the VLT. We see that all those cohort early type galaxies do show inside their central core region such a tangentially biased central orbit distribution, which can be explained by the black hole core scoring process. Okay, so what can we now expect when we think about elliptical core galaxies? We're gonna observe some central missing light visible in their surface brightness profiles. They are gonna be slow rotators due to their diverse merging history. So this means that we will see some low velocity signal in, for example, in this case here, in the order of around 30 kilometers per second. They are expected to host the most massive black holes in the local universe, again, due to their merging history. They are going to show a complex orbit structure, and we already saw that by studying the anisotropy profile of those galaxies, we can get hints about the evolutionary past. And these objects will be intrinsically triaxial. What does this mean? These are ellipsoidals where all the three principal axis lengths, A, B, and C, are different, which makes them quite complex objects to study. And in order to get information about their intrinsic orbit and mass distribution, like for example, also in order to determine the central black hole mass, it therefore requires precise dynamical modeling machineries that are able to deal with the intrinsic triaxial gravitational potential. One method in order to construct such a dynamical model is the Schwarzschild's orbit superposition technique. And in this Schwarzschild orbit modeling, what we aim to do is we want to recover the three-dimensional intrinsic structure of the galaxy under study, for which we, of course, always only have two-dimensional input data. So we can observe the galaxy photometrically and spectroscopically, then providing us with the kinematics of the galaxy. And those two-dimensional input data can be provided to our model. And as a first step in the modeling routine, we will assume an a priori unknown gravitational potential for the galaxy. This gravitational potential will consist of all the relevant contributions. So we, at the beginning, will assume a black hole mass in the center, a stellar, as well as a dark matter contribution to the total gravitational potential. In this assumed potential, we then let thousands of orbits evolve with time, and then we can compute the modeled line of sight velocity distributions, so the modeled kinematics of the computed orbits, and compare these kinematics with the real ones from the spectroscopic observations, and determine a best fit, meaning we want to find the minimum in the discrepancy between the modeled and observed kinematics. And by doing so, we will then get the correct parameters for the gravitational potential that underlies the observed kinematics of the galaxy. So with this, we aim to recover the intrinsic orbit distribution as well as the mass distribution of our galaxy. When we look at the status quo of the dynamical modeling routines so far that were found in the literature, we see that the majority of those models used axisymmetric assumptions, meaning they, for a simplification, assumed that two of the three principal axis lengths would be different, which is not true for the most massive ellipticals. And by applying those axisymmetric models to mock observations of triaxial galaxies, it was shown that the stellar mass to light ratio, as a fitting parameter of the model, can be underestimated by up to 50%, which as a consequence then also leads to a bias in recovering the black hole mass by a factor of around 2. There are, in fact, two other triaxial dynamical Schwarzschild models that can be found in the literature. And when those were applied to galaxies from the Illustri simulation, it was shown that the stellar mass to light ratio can be underestimated by around 24%. And if there was a black hole mass test included, it had a huge discrepancy uncertainty factor of around 5 to 10. So at the beginning of my PhD time, it was therefore not known whether one in principle can unambiguously recover the three-dimensional structure of those triaxial galaxies, given the always only two-dimensional observational data. So it was not known whether this problem is so degenerate that one will never be able to correctly recover the intrinsic structure. And in order to answer this, I now developed a new triaxial dynamical modeling machinery that I called SMART, and then extensively tested it by application to a high-resolution and body merger simulation, including supermassive black holes. And I chose the simulation specifically for this purpose because it is able to accurately compute the dynamics also close to the black holes due to an algorithmic chain regularization scheme. So the new code SMART is the abbreviation for structure and mass recovery of triaxial galaxies. And our code stands out in terms of some benefits. I do not want to go into too much technical details here, but just mention some of the highlights. So we are using non-parametric deprojection routines that allow us to deal with the degeneracies or minimize the degeneracies that are hidden in the triaxial deprojections. We always model full and the non-parametric line-of-sight velocity distributions that provide us then with more kinematical constraints than, for example, when only using Gauss-Hermite parameters. And when determining the best fit model, we take the individual model's degrees of freedom into account, so the model's flexibility to fit the kinematics. And we saw that by doing so, and not only computing the minimum in the chi-squared deviation, we saw that this resolves some bias. I tested 4 different tested projections for this n-body merger simulation. And I show you one example for a projection here. So here we can see the velocity and velocity dispersion sigma map in the top row for the intermediate axis projection of the simulation. And then in the bottom row, we can see the accurately matching fit by SMART to the simulation. And what we now find is that we are able to recover the correct black hole mass as well as the correct stellar mass to light ratio of this tested simulation with a very high accuracy on a 5 to 10% level. On the right-hand side, I show you a bit more detail to our dynamical modeling results. So what do we see here? These are the chi-squared minimization curves, which means that for every tested projection, we compute around 3,000 models. And for these 3,000 models, we always vary the input parameters. So here we vary the tested black hole mass, stellar mass to light ratio, dark matter halo, etc. And for each of these models, we then compute the minimum of the deviation between the modeled and observed kinematics at the degrees of freedom of the model. So this is the so-called archaic information criterion, the AICP. And here in this case, I plotted against the different tested black hole masses of the models. And we see that the minima of these curves, which correspond to the best fit models, then only scatter within a very small variation range around the true black hole mass of the simulation, here marked in red, which is around 1.7 times 10 to the 10 solar masses. We also find that we are able to recover the correct intrinsic kinematics of the simulation with a deviation of beta of only 0.05. We see here the anisotropy profile, with which we already are familiar now with, of the simulation in red that symbolizes or resembles a realistic beta profile for those quadrular type galaxies. We see that there is this tangentially biased central orbit distribution. And our model, so the average we can see here plotted in black, now perfectly follows the real one from the simulation. So with these tests, we were able to show that we are actually able to unambiguously recover the three-dimensional intrinsic structure with a very high accuracy on a 5 to 10% level. And this was also of high scientific interest because with this we proved that in general, the projected kinematics of triaxial galaxies only hold minor degeneracies, which allows an almost unique recovery of the structure and mass, which was unknown so far. And the prerequisite for this is that we have precise kinematic data and that the dynamical modeling machinery is working bias-free and in an accurate way. This then sets the basis to now reliably apply the new technique to real observational data. And I here will show you one example that we analyzed, which is a particularly interesting case. So in this image, you see the massive elliptical core galaxy NGC 5419, observed at a distance of around 60 megaparsecs. And when we look at its surface brightness profile, we see that it already shows a clearly depleted central stellar density core. When we, however, now look at HSD data, we see that there is a double nucleus visible in the center. And this suggests that in this galaxy, there might be a not yet merged black hole binary, which would be a bit in contradiction with what we expect when looking at the surface brightness profile, because so far it was always assumed that the construction of the core and the merging of the black holes would be of one single temporal origin, as described earlier. So we now wanted to find out whether we really do see here a not yet merged supermassive black hole binary. So if this nuclei points to a binary, and we want to find out in which core formation phase is this galaxy observed in. In order to do so, we got high resolution kinematic data by using MUSE of the VLT, and we can see the velocity maps of this galaxy here on the left-hand side. And on the right-hand side, we see that our modeling code is able to fit this galaxy. And we do now find a particularly interesting beta profile, because in this galaxy, we see that inside the central core region, the anisotropy is around 0, which means that we still have an isotropic central orbit distribution. This is in clear contrast to all the other quad early type galaxies that we have so far detected, which all showed the tangentially biased central orbit distribution as explainable by the black hole core scoring process. So what's going on here? It's the first galaxy that we observed with the core and a still isotropic central orbit distribution. Luckily, some recent n-body merger simulations can provide some possible explanation for this, because they suggest that the formation of the core actually happens in two distinct phases. In a first and quite rapid formation phase, the two black holes of the progenitor galaxies would rapidly sink towards the center, which then causes the surrounding stars, due to dynamical friction, to move to larger radii. And this would be the main drive for the quick formation of the depleted central stellar density core, which would happen in a time span of around some tens of mega years. And only afterwards, when the two black holes have already formed a hard binary, the black hole core scouring process would then afterwards slowly change the core orbital structure from isotropic to tangential. And this would be a much more prolonged process in the order of some hundreds of mega years up to a gigayear. This suggestion by the n-body merger simulations, however, has so far never been observationally confirmed. And with NGC 5419, we got the perfect candidate to shine some light on this from an observational point of view, because we see that this galaxy has already undergone the first core formation phase, but the slower second phase of the black hole core scouring process has just begun. So it's the first galaxy observed at such an incomplete merger state at the beginning of the black hole core scouring process. With this, we were able to prove that this galaxy does host a supermassive black hole binary that is not yet merged. And we find a total black hole mass of this galaxy of 1 × 10⁻⁻⁻⁻⁻ solar masses, making this galaxy host to one of the galaxies with the most massive determined black holes ever found in the local universe. We can now talk about why it is important to hunt these ultramassive black holes in the local universe, because this will have the possibility to touch some still unanswered questions that are currently under debate. For example, we want to, of course, find out how massive can the most massive black holes in our local universe be. From this, can we get some constraints on the black hole seas, which is also a current topic that is still under debate. We would like to find out how and where are they distributed. Do they follow fundamental scaling relations with their host galaxies? And the list goes on. What we do expect to see that we find ultramassive black holes in at least an order of 10 to the 10 solar masses, as predicted from distant quasar observations. These objects, however, were for a long time not observed and not found. And one of the reasons for this was that in order to hunt them, the so-called black hole scaling relations were used, because in the last 2 decades, we found that the black holes in the center of the galaxies do follow some fundamental scaling relations with their host galaxies, pointing to a co-evolution between them. And here we see the famous black hole sigma relation, which means that the higher the velocity dispersion at the half-light radius of the host galaxy is, the higher the black hole mass is that we find in the center of this galaxy. And when we now look at the ultramassive black hole regime, like in the order of 10 to the 10 or above, we see that if we would like to find those objects, we would, by following this relation, expect them to be found in some quarter type galaxies with a very high velocity dispersion sigma in the order of 500 or more kilometers per second. And these galaxies simply do not exist. This is why only very slowly the sample of the ultramassive black holes that were found got collected. And we see that if there was an ultramassive black hole found, it had either huge error bars, or in general, these measurements actually do lie above the actual black hole sigma relation that we so far found for the local universe. These measurements were mainly done with axisymmetric dynamical modeling routines. And as we heard before, these can have some bias when they applied to the most massive objects. And therefore, it was not clear whether we can trust these measurements. And this strengthens also the idea that it is important to now apply a triaxial modeling machinery that was extensively tested so that we can trust these measurements. And I here now plot our measurements done with SMART. The red one is the NGC 5419 galaxy, and then the pink one is another measurement that was done with SMART. And what we find is that also our values do actually lie above the sigma relation. And again, some simulations now provide an explanation for this, because they say that it is actually somehow expected for the most massive objects to lie above the relation, because with the virial theorem, one can show that in those dry merging processes, the sigma of the remnant galaxy will be staying around the same compared to the progenitor galaxies, while of course the mass of the black holes would add up. So we actually do expect a shift of the black hole sigma relation. And the next thing, of course, would be to fill this regime here at the high mass end with more observational data points to find out what is the exact black hole sigma relation and other fundamental relations in this mass regime. Another cutting-edge field of science that we can touch with our dynamical models has to do with the stellar initial mass function. The stellar IMF is the initial distribution of the stellar masses inside a galaxy. And for a long time, it was believed that the IMF we find in the Milky Way would be universal and also true for other different kinds of galaxies. So we find that the stellar initial mass function for the Milky Way would follow a so-called Krupa IMF, which is a power law for the higher masses. So what we see here in this plot is the number of stars plotted against the mass regime for the stars. And we see that it follows a power law at the higher mass regime and then turns over to a shallower slope in the slower mass regime. Some techniques, like for example, the stellar population modeling method, or also dynamical modeling results, however, found that the IMF that we determine in the most massive quad early type galaxies show a different IMF to what we see in the Milky Way. So we saw that in these quad early type galaxies, we find a so-called bottom heavy IMF, which would mean that there are more dwarf stars in the central region. So more or less a single power law, so-called salpeter IMF. These results, again, were a bit contradicted by what strong gravitational lensing results would find, which also would try to get some constraints on the IMF. And what we can now contribute to solving this, or shine some light on this, is that, as described before, we can find out the stellar mass to light ratio as a fitting parameter with our models. And this, of course, also puts a constraint on the IMF. So in general, we can say the higher the stellar mass to light ratio, the more bottom heavy the IMF would be. And historically, what was always done is that we determine one single stellar mass to light ratio fitting parameter in our models. And when I do so in NGC 5419, I get a M/L ratio of around 6. That would be something in between a salpeter and a Krupa IMF. But now some recent results show that there might be some radial gradient in the IMF in these galaxies. And when I allow the smart routine to fit such a radial M/L gradient, we see that the model actually prefers an IMF that is more or less a salpeter IMF in the central regions and then drops down to a more Krupa-like IMF in the outskirts. And this holds the potential to maybe solve a bit the discrepancies explained by the other routines determining the IMF, because we see that with this, the IMF measurements can clearly depend on the radius where these measurements are done. And if we now wonder whether this has an impact on the black hole masses that we determine, the answer is luckily no. So in both cases, when allowing for such a gradient or also not allowing, we do find a black hole in the order of 1 × 10⁻⁻⁻ solar masses. So this is a quite stable result. One more interesting finding we see is or has to do with the formation of the kinematically distinct cores, the so-called KDCs in quarter type galaxies. So when we look again at the velocity map of our galaxy, NGC 5419, we see that there is a counter-rotating signal in the center of this galaxy. So we here see that the rotation flips compared to the overall rotation in the outskirts. This is quite common to be observed in quarter type galaxies, and it can also be seen in some power law ellipticals. And in those smaller power law ellipticals, the construction of the KDC can be explained by a dissipative origin, which is not true for the dry merging history of the most massive ones. And it was also shown that in the quarter type galaxies, the stellar population inside these KDCs is not different from the stellar population in the outskirts. So it was not known how these KDCs in those most massive ellipticals can be constructed. The advantage of our modeling is that we can now project our best fit models to various projection axes we want to test out. And I here show you a projection of our best fit model along the major axis of the galaxy and along the minor axis of the galaxy. Why do I do this? Because with this, I see that this kind of twisted KDC signal is simply a projected overlay of orbits rotating in this direction, which are visible along the major axis, and another group of orbits rotating along this direction, also causing such a counter-rotating signal that is visible along the minor axis. So in simple terms, this means that what we see here, the twisted KDC, can be seen as a projected overlay of some orbits rotating around 2 different axes. I repeated this analysis for an embodied merger simulation, also showing such a twisted KDC signal. And I find the same observation, that we also can explain this by orbits rotating around 2 different directions. And for this simulation, it was shown that these counter-rotating orbits can be seen as the result of angular momentum flips that the black holes experience during the merger process. And due to the fact that the stellar nuclei will follow, if they are bound to the supermassive black hole, the movement of the infalling black hole motion, we will then be able to see this counter-rotating signal. And the idea now is, of course, that what we see in NGC 5419 can also be described by such a stellar dynamical origin due to the infalling black holes that shows such a flip. And in order to strengthen this idea, I now compute the stellar mass that is responsible for this KDC signal. I call this now KDC mass. And I plot it against the black hole mass for a sample of embodied merger simulations that show a variety of black hole masses. And I also add our data point for NGC 5409, and I see that there is a correlation between the KDC mass and the black hole mass, strengthening the idea that the KDC mass is a direct result of the supermassive black hole infalling process. And again, the idea now would be to strengthen this observationally, meaning we want to get a larger collection of observational data points for this diagram and some quad-early type galaxies like the well-known M87 showing such a KDC, or another one for which we already have some high-resolution MUSE data would be the next step then to analyze. Okay, this brings me to the take-home messages for today. So we saw that the intrinsic properties of triaxial ellipticals in general can be unambiguously recovered. We saw that NGC 5419 is the first galaxy observed at an incomplete merger state at the beginning of the black hole core scouring process, hinting to the fact that this galaxy hosts a still not yet merged supermassive black hole binary. And we find a total mass of around 1 × 10⁻⁻10 solar masses, making it to one of the most massive ones determined so far in the local universe. We saw that the IM or stellar mass to light ratio measurements point to a possible radial IMF gradient in the quad ellipticals. And we saw that their KDCs can be produced by flips of black holes with the bound stellar nuclei during the dry merging process. Okay, thank you for listening, and I'm happy to take questions.
Okay, so are there any questions from the audience?
So for NGC 5419, what is the amount of dark matter that you find in the center? Yeah. And what is the surface density, stellar surface density? Is particularly high there, or do you have a number in mind?
So first of all, what we fit are some generalized NFW halo profiles in our dynamical modeling routine. So it is a NFW halo profile with a flexible slope in the center. And we do find that the center's slope would be a constant. So we do find also some kind of core in the central dark matter halo profile, and more or less it resembles of what is assumed for a normal NFW. For the dark matter, so you mean the dark matter in comparison to the stellar? I think some prepared now where we compare the total dark matter mass with the stellar mass. So in principle, the stellar mass does show this core. So there is less stellar mass than we would actually expect for the power law ellipticals. And at the around half-light radius, the dark matter would be then dominant over the stellar mass. In terms of fractions, I would need to look it up. Yeah.
You have an idea? That was the second part of the question. So yeah. Do you have an idea what is the stellar surface density? So it's particularly high. So the solar masses per kiloparsec square or something like that in the center?
At the moment, I don't have a number in mind. I would need to look it up. Yeah. Thank you.
Thank you. More questions in the room?
So, hi, thanks for the talk. So what's the size of the cores you were mentioning for dark matter? I mean, are they like of the order of kiloparsecs or more? Or?
Sorry, say again.
I mean,
the
for the dark
size
matter
of the-
course you were mentioning, I mean, what's the size of this course? Because I'm not sure if in such massive galaxies you would expect cores or not. Or...
For the dark matter?
Yes.
So you mean where the halo would
Yeah, so
get
like the
better?
range over which the slope is constant, the inner slope.
Um,
And you're referring to projected cores? Or, I'm not sure. There, yeah.
so
Right.
we do have so what we use is we get the inner density slope that is constant. I have to check at which radius this happens.
Right. I mean, you know if these are physically expected from simulations or not? Or?
Yes.
Okay.
Yes. So I mean, especially for our tests, right? We have the complete or the exact comparison actually to the embodied simulation, and we prove this if our models can recover the one that was computed by the simulation and it matched.
So does this include, for example, hydrodynamical effects, feedback effects, and that? I mean, I suppose it should be efficient, right?
This is not concluded in the
Right.
simulation.
Okay.
Yeah, it's not a hydrodynamical
Yeah, I see.
simulation.
Okay, thanks. And also, so for this course that you're saying, is it necessary to have this kind of merging process, or can even a single massive black hole form a core, even if it's smaller? Is that possible or not?
So if it's possible to have a core without the merging process, you mean?
Yes.
Not that I know of. I mean,
Okay.
the chord objects we do find, we assume that this is the result of some dry merging.
Right. Because I know in embodied simulations of globular clusters, which are much less massive, obviously, I mean, they do predict like kind of like mini cores.
Are you talking about the dark matter core?
Oh, sorry, no, not sorry. Now I'm talking about the photometric
stellar.
cores, which are assuming smaller, right? So yeah,
The stellar one.
yeah, the stellar one
Yes.
produced by the black holes.
Yeah.
Yeah.
As far as I know,
Okay.
the explanation for those cores observed in the most massive
Okay.
ellipticals
I'm
are
sorry.
always
One last
better.
question. I mean, are these scores significantly higher than the radius of influence of the black holes individually?
Yeah,
Right.
this is another good question. Another scaling relation that we do find is that actually the core radius is almost always exactly the sphere of influence of the black hole. Yeah, and this correlation actually is also true for the high mass end. So you saw that this black hole sigma relation thus has this offset, and when we repeat this for the plotting the core radius against the sphere of influence, we see that this is actually a constant relation where the high mass black holes also fit in. Yeah.
Okay, thank you.
And again, this strengthens the idea that this is linked to the black holes. Yeah.
Thank you. More questions?
Hi, many thanks for the nice talk. According to what I understood, you were fixing the dark matter inner slope to 0, right? And the scale radius also to 40 kiloparsec,
Yes,
I think.
exactly. Yeah.
Okay, do you have any idea if you allow for Caspian profiles, would it change the mass of your black hole just by a little bit, or not at all? Or why do you fix those two parameters?
Yeah, we check this and we find that especially when constraining the black holes, it has almost no influence, because inside the sphere of influence, the black hole is so dominant that the dark matter has very little effect on this. But we did check it and tested different halo profiles out, and yeah.
Okay, thank you. And another very fast question. When applying Schwarzschild modeling, you need to assume dynamical equilibrium, right?
Yes, exactly.
But you were talking about this observed system with the two stellar nucleus and black holes and everything.
Yeah.
Do you have any idea how good is the assumption of dynamical equilibrium in this kind of galaxies? Or
good question. So this example is a bit cutting the edge of what is possible with dynamical models, because as you say, we do need to assume dynamical equilibrium, and it was a test actually to find out whether it is in principle even possible to get a model for this galaxy. And why we do believe that it is possible, first of all, the fits look great, so we are able to find a model for this galaxy. We also, for example, what we always do is we always model the galaxy at least twice, like we are providing once one half of the kinematic data, repeating it for the same mass, for the other half. We get the same results in both cases. Yeah, but it is a bit an edgy case here. Yeah.
Hello. Any idea how the presence of gas can change all of this picture about the Caspi and the cores in elliptical galaxies? Because I believe if you have gas, the gas goes to the center very fast, very quickly, produce starbursts, produce stars, and probably increase the core or dilute the core to the Caspi. But do you know any idea about that?
So what I know is that in these galaxies, we really expect very, very little amount of gas. So we do not see that at some point there will gonna again be a cusp that is coming out of the center due to some new star formation. Yeah, so they are so old and have already undergone so many mergers that we can expect to almost ignore the gas. Yeah.
So any more questions? If not, we can thank the speaker again.
Thank you.